This is an audio recording for visually impaired students from the book Selected Topics in Inorganic Chemistry by S. Chan. Non-aqueous solvents. Introduction. Most of the chemical reactions familiar to us take place in aqueous solution since water, due to high value of its dielectric constant, has an increased ability to dissolve the ionic compounds and many other substances. However, there are many chemical reactions which cannot be carried out in aqueous solution but can be studied in a non-aqueous medium. A large number of non-aqueous solvents have been discovered in the last few years. These solvents have a sizable value of their dielectric constant and hence can dissolve many substances. Examples of such solvents are anhydrous liquid NH3, liquid SO2, anhydrous HF, liquid N2O4, etc. Classification of solvents. Solvents have been classified in a number of ways depending on the properties of the solvents. The most convenient classification of solvents is based on the electrolytic characteristics of the solvents. This classification has been shown below. Classification of solvents. First, non-ionizing solvents, and second is the ionizing solvents. Non-ionizing solvents are non-polar liquids and aprotic solvents. Example, benzene, carbon tetrachloride. Ionizing solvents, polar liquids. They are polar liquids and further classified into protonic and non-protonic. Non-protonic example, liquid SO2, BRF3 and HgBr2. Then protonic are further classified into three. First, protogenic, second, protophilic, and third, amphiprotic. Protogenic are acidic solvents which have strong tendency to donate protons. Examples, H2SO4, H2F2 and CH3COOH. Protophilic, they are basic solvents and strong affinity to accept protons. Examples, liquid NH3, pyridine, ethylene diamine. Next is amphiprotic. They are amphoteric solvents and can act both as acids or bases. Examples, H2O and CH3OH. The classification shown above gives the following types of solvents. First, non-ionizing solvents or non-polar solvents. These solvents are also called aprotic solvents or non-protonic or non-protic solvents. These solvents have no hydrogen in their structure. Examples are C6H6, CCl4, etc. Second, ionizing solvents. Polar solvents, examples, ionizing solvents or polar solvents. Examples of such solvents are H2SO4, H2F2, CH3COOH, H2O, liquid NH3, liquid SO2, pyridine, BRF3, HgBr2, CH3OH, etc. Because of their polar nature, these solvents have associated structures. Non-polar substances do not dissolve in these solvents because of the squeezing effect produced by their associated structure. However, ionic and covalent polar substances dissolve in them. The dissolution of ionic substances is due to their greater solvation energy than the lattice energy of the salts. Several covalent substances dissolve forming hydrogen bonds. Classification of ionizing solvents. First, protonic solvents. These solvents have hydrogen in their structure. These may be of the following types. A. Protogenic solvents or acidic solvents. These solvents have a tendency to donate protons. Examples are H2SO4, H2F2, CH3COOH. These solvents are also called acidic solvents. B. Protophilic solvents or basic solvents. These solvents have a tendency to accept protons. Examples are liquid NH3, pyridine, ethylene diamine, etc. These solvents are also known as basic solvents. C. Amphiprotic or amphoteric solvents. These solvents show dual nature, that is, they can lose as well as accept protons depending on the nature of the reacting species. Example, H2O, alcohols, liquid NH3 and CH3COOH, etc. Amphoteric solvents undergo autoionization, self-ionization, in which a proton transfer between two similar neutral molecules takes place and a cation and ion pair of the solvent is obtained. Second, non-protonic solvents. These solvents have nothing to do with protons. Examples are liquid SO2, BRF3, HgBr2. Due to self-ionization, they also furnish cations and anions similar to protonic solvents. In this chapter, we shall restrict our study on ionizing solvents only, that is, in which inorganic substances ionize and give ionic reactions, as in H2O. Non-ionizing solvents are of great interest in organic chemistry. Physical properties of solvents and their role in chemical reactions. Every liquid cannot be used as a solvent in a chemical reaction. Here we therefore concentrate ourselves on the properties of a solvent which makes the solvent suitable for using it as a good solvent. Here we shall also compare the properties of some non-aqueous solvents with the properties of H2O. Some important properties of a solvent which make the solvent a useful solvent in chemical reactions are discussed below. First, melting point and boiling point. Most of the chemical reactions are carried out in liquid phase, hence the melting and boiling point of a solvent indicates the range of temperature within the solvent can be used. Melting point and boiling points in degrees Celsius of some solvents are given below. H2O 0.0, 200, NH3 minus 77.7 to minus 33.4, SO2 minus 75.5 minus 10.2, HF minus 89.3, 19.5, and CH3COOH 16.16 and 118.1. These values show that H2O has a very convenient liquid temperature range between 0 and 100 degrees Celsius. CH3COOH can act as a solvent at ordinary temperature range 16.16 degrees Celsius to 118.1 degrees Celsius. NH3 and SO2 exist as gases at ordinary temperature and pressure and hence act as solvents only at low temperatures. Second, heat of fusion and heat of vaporization. The heat absorbed by 1 mole of a substance to change from solid to liquid state is called its molar heat of fusion. Solid to liquid, delta H is equal to heat of fusion is equal to positive delta H of fusion. Similarly, the heat absorbed by 1 mole of a substance to change from liquid to vapor state is called its molar heat of vaporization. Liquid to vapor, delta H is equal to heat of vaporization is equal to positive delta H of vaporization. The heats of fusion and vaporization of a solvent indicate the nature and the strength of forces with which the molecules of the solvent are held together in the solid or in the liquid state. A high value of delta H of vaporization of a liquid indicates that the intermolecular forces in the liquid are strong. The ratio of delta H of vaporization in that the intermolecular forces in the liquid are strong. The ratio of delta H of vaporization in joules and boiling point Tb in Kelvin of a liquid is a constant which is known as Thornton constant, that is delta H of vaporization in joules upon Tb in Kelvin is equal to Thornton constant. For normal liquids, the value of Thornton constant is about 90 joule per Kelvin. Such liquids do not have any bonds between their molecules. Thus, these liquids exist as independent molecules. Value of Thornton constant greater than 90 joule per Kelvin for liquid solvent indicates that the molecules of the liquid are associated. Since the common solvents like H2O, NH3 and HF have Thornton constant value greater than 90 joule per Kelvin, these solvents are associated solvents. These liquids are polar. These values of delta H fusion and delta H vaporization in kilojoule per mole for H2O, NH3, SO2 and HF are given below. H2O 6.02, 40.65, NH3 5.65 and 23.34, SO2 7.40 and 24.93 and HF 4.58 and 30.28. Above values show that values of delta H fusion for H2O and NH3 are almost the same. This means that the forces which hold the molecules of H2O and NH3 are of the same magnitude. Thus, these solvents will serve as similar solvents. It may also be noted that since the value of delta H fusion of SO2 is comparatively high and that of HF is comparatively low, the force holding the molecules of SO2 together is stronger than that holding the molecules of HF is weaker. Third, dielectric constant. Dielectric constant of a solvent determines the ability of the solvent to dissolve polar and non-polar substances in it. We know that the Coulombic force F between a cation and an anion of an ionic compound is given by the expression F is equal to Q1 into Q2 upon E into R1 plus R2 whole square. In this expression, Q1 and Q2 are the charges on cation and anion respectively. R1 and R2 are the radii of the two ions, and E is the dielectric constant of the solvent. The value of dielectric constant depends on the nature of the solvent in which the ionic compound is dissolved. The value of dielectric constant of some solvents are given below. H2O 78.5, 25 degrees Celsius. NH3 22.0 at minus 33.5 degrees Celsius. SO2 17.3 at minus 16 degrees Celsius. CH3COOH is equal to 9.7 at 18 degrees Celsius, and HF 83.6 at 0 degrees Celsius. N2O4 is equal to 2.42 at 0 degrees Celsius. It may be clear from the above expression that if dielectric constant of a solvent is large, then force would be small, and that is, if dielectric constant is large, small amount of energy would be required to separate the ions, and hence it would be easy for a solvent having a high value of dielectric constant to dissolve an ionic compound in it. For example, since anhydrous HF and H2O have high value of dielectric constant, these are the best solvents for ionic compounds. On the other hand, since liquid NH3 and liquid SO2 have low values of dielectric constant, these solvents have smaller ability to dissolve ionic compounds, especially those containing multi-charged ions. Thus, carbonates, sulfates and phosphates which contain multi-charged ions are insoluble in liquid NH3 and liquid SO2. Fourth, dipole moment. Greater is the polarity of the bond in a solvent molecule, greater is the charge separation, and higher will be the value of dipole moment. Substances having high dipole moment values are good solvents for polar solutes. This is because of the fact that greater is the polarity of a solvent molecule, greater is the solvation energy released on dissolution of a solute. Dipole moment value of a solvent also gives an idea about the extent of association of the molecules of a liquid and hence its liquid range. Dipole moment values of H2O, NH3 and SO2 are given below. H2O 1.85, NH3 1.47 and SO2 1.61. Fifth, viscosity. Viscosity gives a measure of the fluidity of the solvent. Solvents like water, carbonate, tetrachloride have low viscosities and flow rapidity under ordinary temperatures. In solvents of low viscosities, the operations such as precipitation, crystallization, filtration, etc. can be easily carried out without any difficulty. With increasing viscosity of a liquid, the difficulty of such operations increases. Solvents like anhydrous sulfuric acid have higher viscosities, and this reduces their usefulness as solvent. Viscosity of H2O, NH3 and SO2 is 1.00, 0.241 and 0.009 respectively. Sixth, proton affinity. It is applicable for protonic solvents only. It greatly affects the behavior of a solute in a given solvent. NH3 has greater proton affinity than H2O. Hence, acetamide CH3CO NH2, which behaves as a very weak base in aqueous solution, show acidic properties in liquid NH3. Proton affinity in kilojoule per mole for H2O and NH3 are 760 and 865 respectively. The properties of H2O, NH3 and SO2 other than those mentioned below are given below. Property equivalence conductance in ohm inverse. For H2O, 6 into 10 raised to power minus 8 at 25 degrees Celsius. For NH3, 5 into 10 raised to power minus 9 at 133.4 degrees Celsius. For SO2, 1 into 10 raised to power minus 7. Critical temperature in degrees Celsius. For H2O, 374. For NH3, 132.4. For SO2, 157.5. Critical pressure. For H2O, 217.7, for NH3 112.0, for SO2 77.8. Density For H2O 0.96, for NH3 0.68, and for SO2 1.46. Types of chemical reactions taking place in non-aqueous solvents. First, metathetical precipitation reactions. The reactions in which precipitate is formed by mixing two solutions of two compounds are called metathetical or precipitation reactions. Thus, precipitation reactions are normally double decomposition. The formation of a precipitate in different solvents depends on the solubilities of the products in those solvents. For example, the precipitate of AgCl is obtained by mixing BaCl2 and AgNO3 in aqueous medium. In liquid NH3, the above reaction is reversed. That is, in liquid NH3, precipitate of BaCl2 is obtained by combining AgCl with BaNO3 whole twice in liquid NH3. Thus, we see that reaction 1 is reversed on changing the solvent. Second, acid-base reaction. We have already said that the ionic solvents are polar compounds and undergo self-ionization. Self-ionization of some important solvents is given below. An acid-base reaction in a non-aqueous solvent can be explained on the basis of solvent system concept of acids and bases. According to this concept, an acid is a substance which contains the solvent cation and a base is a substance which contains the solvent anion. For example, since self-ionization of liquid NH3 gives NH4 positive solvent cation, that is acid ion, and NH2 solvent anion base ion, all ammonium salts will behave as acids in liquid NH3 and all soluble amides will act as bases in liquid NH3. Hence, the reaction between NH4Cl acid and KNH2 base in liquid NH3 shown below is an acid-base reaction. NH4Cl acid plus KNH2 base gives out KCl salt plus 2NH3 solvent. Some examples of acid-base reaction in different solvents are given below. In liquid BRF3 self-ionization, 2BRF3 solvent gives out BRF positive 2 solvent cation acid ion plus BRF4 negative solvent anion base ion. SnF4 reacts with BRF4 negative ion base to produce the solvent cation BRF2 positive. Hence, SiF4 acts as an acid in liquid BRF3. Acid-base reaction. SnF4 acid plus BRF4 negative base gives out SnF6 negative plus BRF2 positive solvent cation. In liquid HF, self-ionization. 3HF solvent gives out H2F positive solvent cation, that is acid ion, plus HF2 negative solvent anion base ion. Acetone and HNO3 both behave as bases in liquid H2F2 since these compounds give HF2 negative base anion in liquid HF. Acid base reactions. CH3 whole twice CO base plus 2HF gives out CH3 whole twice COH positive plus HF2 negative base ion. Acid character of CH3COOH in H2O and liquid NH3. When CH3COOH reacts with H2O in liquid NH3 solvents, H2O and liquid NH3 both accept a proton from CH3COOH to produce H3O positive and NH4 positive ions. Due to the production of these ions, CH3COOH behaves as an acid in both the solvents. Now, since the proton accepting ability of H2O is less than that of liquid NH3, CH3C double bond OH behaves as weak acid in aqueous solution and acts as strong acid in liquid NH3. Comparison of acidic strength of HClO4, HCl, HBr, HI and HNO3 in aqueous solutions. When the given compounds represented as HX reacts with H2O, proton is donated by HX to H2O to produce H3O positive because HX molecules has stronger proton donating property than H2O. Due to the production of H3O positive ion, HClO4, HCl, HBr, HI and HNO3 behave as acids in aqueous medium. In aqueous medium, all the given acid dissociate or ionize completely and hence behave as equally strong acids. Thus, H2O acts as a leveling solvent for the given acids. Here it should be noted that HX and H2O both are protonic substances. Third, solvation reactions. Formation of solvates. Solvation reaction is a general reaction in which a solute, a cation, and an anion or a neutral molecule reacts with one or more molecule of a solvent, example H2O, liquid NH3, liquid SO2, etc., to form a product in which the solute and solvent species are attached to each other by a hydrogen bond or by a coordinate bond. The product formed is called solvate. Solvate is an addition compound and hence is called an adduct. The addition compound contains solvent of crystallization. In the formation of a solvate, the solvent acts as a Lewis acid while the solute species behaves as a Lewis acid. When the solvent used is water, the solvation reacts is called hydration and the addition compound formed is called hydrate. Hydrate contains one or more molecules of water as water of crystallization. Similarly, when the solvent is liquid NH3, the reaction is called ammoniation and the addition compound formed is called ammoniate. Ammoniate contains one or more molecules of ammonia as ammonia of crystallization. Fourth, solvolytic reactions. Solvolysis. Solvolytic reaction are the reaction in which the solvent molecule react with the solute molecule, salt or ion in the way which consists of the following steps. A. The solvent molecule undergoes autoionization or self-ionization to give solvent cations and solvent anions. B. The solute or salt splits into solute cations and solute anions. The solute cations or solute anions interact with the solvent cations or solvent anions. Due to this interaction, the concentration of the solvent cations or solvent anions is increased. When H2 and NH3 are used as solvents in the solvolytic reaction, these reactions are called hydrolysis and ammonialysis or ammonialytic reactions respectively. Liquid ammonia. Introduction. Liquid ammonia or liquid NH3 is a protonic solvent since it gives a proton H positive on ionization. NH3 gives out H positive plus NH2 negative. It is a highly useful solvent and a number of chemical reactions are carried out in this medium. The value of dielectric constant of liquid NH3 is 22.0 at minus 34 degrees Celsius is much smaller than that of water 78.5 at 25 degrees Celsius and hence liquid NH3 has decreased ability to dissolve ionic compounds. The liquid range for liquid NH3 is from 34.0 degrees Celsius to minus 77 degrees Celsius, boiling point minus 34 degrees Celsius and melting point minus 77.7 degrees Celsius. Solubility of various substances in liquid NH3. A. Solubility of ionic compounds in organic salts. We know that ammonia has a low value of its dielectric constant. This low value suggests that liquid ammonia has a poor ability to dissolve ionic compounds. Ammonium salts and most of the nitrites, nitrates, cyanides, thiocyanates, perchlorates are soluble in liquid ammonia. Salts containing highly charged ions are insoluble. Fluorides and chlorides except Be2 positive and Na positive chlorides are practically insoluble. Bromides are less soluble while iodides are freely soluble. Thus the solubility of the halides of a given metal increase in going from fluoride to iodide. Most of the metal amides are insoluble. The salts of some metals react with liquid ammonia and form amine complexes. B. Solubility of non-ionic compounds, organic compounds. Halogen compounds, alcohols, ketones, esters, simple ethers, amines, phenol and its derivatives, etc. are soluble. Alkanes are insoluble. Alkenes and alkynes are slightly soluble. In this sense, liquid ammonia is a better solvent for non-ionic and non-polar compounds. C. Solubility of nonmetals. The nonmetals like sulfur, phosphorus, iodine, etc. are soluble and they react with the solvent. D. Solubility of alkali metals and alkaline earth metals. All the alkali metals and alkaline earth metals excepting beryllium are soluble in liquid ammonia. 100 gram of liquid ammonia dissolves 10.9 gram of lithium, 24.8 gram of sodium, 46.8 gram of potassium, all at minus 33 degrees Celsius, and 334 gram of cesium at minus 50 degrees Celsius. Thus, we see that the solubility of alkali metals in liquid ammonia increase as we pass from lithium to cesium. The solution obtained by dissolving alkali metals in liquid ammonia has the following characteristics. First, color of the solution. The color of the dilute solution is deep blue. As the concentration of the solution increases, the blue color changes to bronze, which disappears on the further increase of the concentration of the solution. The color of the solution is independent of the metal dissolved in liquid ammonia. The blue color of the dilute solution is due to the formation of ammoniated metal cation and ammoniated electron in it. Second, decomposition of very dilute solutions. Very dilute solutions of the alkali metals in liquid ammonia is metastable, since in the presence of a catalyst like Fe2O3, its ammoniated electron undergoes decomposition. Third, evaporation of the solution. When alkali metal ammonia solution is evaporated, alkali metal dissolved in the solution is recovered. Fourth, paramagnetic character. Dilute solution of alkali metals in liquid ammonia is paramagnetic, which is due to the presence of unpaired ammoniated electrons in the solution. The susceptibility of the solution falls down as the concentration of the solution increases, and ultimately the solution becomes diamagnetic. Paramagnetism reappears at higher concentration of the solution. Fifth, electrical conductivity. The electrical conductivity of the very dilute solutions is high and is in the range of fully ionized salts in water. The high conductivity is due to the presence of ammoniated electrons in the solution. It decreases with concentration up to about 0.05 amp, but then rises sharply. The concentrated bronze solution has conductivities in the range of metals. Sixth, density. Dilute solution has very low density. Low density is due to the fact that ammoniated electrons present in the solution are supposed to occupy the cavities or holes within ammonia molecules. Seventh, reducing property of dilute solution. We have said above that the blue solution of alkali metal in liquid ammonia contains ammoniated electrons. These ammoniated electrons reduce various substances. Thus, dilute solution of alkali metals are reducing agent. In this reaction, the alkali metal is oxidized to some alkali metal salt. The reducing property of alkali metal in liquid ammonia has been used to synthesize useful compounds which are otherwise difficult to prepare. For example, many covalent hydrides react with metal ammonia solution to produce metal salts that are stable in liquid ammonia. In inorganic synthesis, metal ammonia solution react with conventional transition metal complexes to give complexes in which the central metal atom has oxidation number 0. Autoionization of liquid ammonia. Liquid ammonia ionizes in the following 3 steps. A. NH3 gives out H positive plus NH2 negative. H positive plus NH3 gives out NH4 positive, and the result is 2NH3 solvent gives out NH4 positive ammonium ions plus NH2 negative amide ions. B. 3NH3 solvent gives out 2NH4 positive ammonium ions plus NH2 negative imide ions. C. 4NH3 solvent gives out 3NH4 positive ammonium ions plus N3 negative nitride ions. Amino acids and amino bases. Different modes of autoionization of liquid NH3 given above indicate that according to solvent system concept, in liquid NH3, any substance that gives NH4 positive ions, which are solvent cations, will act as an acid in liquid NH3, while that which produces NH2 negative or NH2 negative or NH2 negative or N3 negative ions, which are solvents anions, will behave as a base in liquid NH3. The compounds which give NH4 positive ions in liquid NH3 are called amino acids, while those which give NH2 negative or NH2 negative or N3 negative ions in the solvent are called amino bases. Example of amino acids: ammonium salts, organic amides, acetic acid, sulfamic acid, etc. All act as amino acids in liquid ammonia since they produce NH4 positive ions in this solvent as given below. It may be noted that since H2N SO2 OH produces two NH4 positive ions, this acid behaves as dibasic acid in liquid ammonia. Examples of amino bases: KNH2, PBNH, and BIN are the examples of amino bases since these compounds give NH2 negative, NH2 negative, and N3 negative ions respectively in liquid ammonia. Reactions of amino acids. First, neutralization reaction. These reactions have been discussed on the subsequent pages. Second, reaction with metals. Acids give out H2 with metals in aqueous solution. In a similar way, ammonium salt which act as acids in liquid ammonia give H2 when they react with metals in liquid ammonia. Third, decolorization of blue solution. Ammonium salts decolorize blue solutions of alkali metals in liquid ammonia. Fourth, metathetical or precipitation reactions. When an amino acid like NH4Cl, NH4Br, NH4I, or NH4 whole twice S, etc., is mixed with the liquid ammonia solution of a metallic salt like SrNO3 whole 2, ZnNO32, AgNO3, or CuNO3 twice, CdNO3 twice, Ki, etc. The salt of the metal is precipitated. Fifth, reaction with metal oxide and metal hydroxide. Amino acids are able to dissolve metal oxides and metal hydroxides. Sixth, decomposition of salts. Amino acids can decompose salts of weaker acids. Reactions of amino bases. First, extremely strong bases such as H negative and O2 negative are leveled to NH2 negative ion in liquid ammonia. Second, precipitation reactions. When an amino base like KNH2 is mixed with the liquid NH3 solution of a metallic salt like AgNO3, PbI2, BiI3, etc., the amide, imide, or nitride of the metal is precipitated. Third, complex formation reactions. When metal salts and metal amides react with excess of KNH2 in liquid ammonia, soluble amido complexes are formed. Fourth, NH2 negative ion can pick up protons from very weak acids and form salts. For chemical reactions taking place in liquid ammonia. Chemical reactions that take place in liquid ammonia are of the following types. First, metathetical or precipitation reactions. Example of some precipitation reactions taking place in liquid ammonia are given below. First, chlorides. Chlorides are precipitated by the following reactions. Second, bromides and iodides. Third, amides, imides, and nitrides. Third, sulfides. Fourth, barium alcoholate. Second, acid-base neutralization or salt formation reactions. In liquid ammonia, acid-base neutralization reaction is that in which a compound containing or making available NH4 positive ion amino acid combines with a compound containing or making available NH2 negative or NH3 negative ion amino bases to form the salt and the solvent. Actually, the above reactions take place through the following steps. NH4Cl gives out NH4 positive and Cl negative in presence of liquid ammonia. Similarly, KNH2 gives out K positive and NH2 in presence of liquid ammonia, and the final product is solvent cation, that is NH4 positive plus solvent anion NH2 negative gives out solvent, that is 2NH3 in the presence of liquid ammonia. Equation 1 indicates that neutralization reaction in liquid NH3 can also be defined as the combination of solvent cation and solvent anion to form the unionized solvent. Other example of acid-base neutralization reactions taking place in liquid ammonia are listed below. Comparison of the process of neutralization reaction in an aqueous solution and liquid ammonia. In aqueous solution, the process of neutralization reaction of a strong acid by a strong base is the combination of H3O positive and OH negative to form unionized H2O. A similar thing happens in case of liquid ammonia. In liquid ammonia, the process of neutralization reaction is the combination of NH4 positive and NH2 negative or NH3 negative ion to form an unionized NH3. For example, the neutralization reaction between NH4Cl and KNH2 can be shown. Thus, we see that the role of NH4Cl in liquid ammonia is the same as that of HCl in aqueous solution. Similarly, the role of KNH2 in liquid ammonia is the same as that of KOH in aqueous solution. Thus, NH4Cl may be regarded as strong acid and KNH2 as a strong base in liquid ammonia. Above discussion shows that substances producing H3O positive ions in H2O are acids. Similarly, ammonium salts giving NH4 positive ions in liquid NH3 are acids. The substances producing OH negative ions in H2O are bases, and the substances containing NH2 negative or N3 negative ions are bases in liquid ammonia. The course of neutralization reaction occurring in liquid ammonia may be followed by means of conductometric titration and in certain cases through indicators. For example, phenolphthalein is colorless in liquid ammonia but develops an intense red color in presence of alkali amides. Third, amphoteric behavior of ZnNH2 whole twice in liquid ammonia. ZnNH2 dissolves in amino acids as well as in amino base in liquid ammonia and hence is said to show amphoteric character in liquid ammonia. Fourth, ammonation reactions or formation of ammoniates, that is solvation reactions or formation of solvates. In the general discussion of solvation reactions, we have already said that solvation reaction in which liquid ammonia is used as solvent is called ammonation reactions and the solvate formed is called ammoniate. In the formation of ammoniates, liquid ammonia acts as Lewis base and the solute behaves as a Lewis acid. The formation of some ammoniates in liquid ammonia has been shown below. The ammoniates may be 1:2 or 1:1 adducts. More examples of ammoniates formed by liquid ammonia with inorganic salts are MgI2.6NH3, NiI2.6NH3, NaI.4NH3, etc. In the formation of these ammoniates, NH3 molecule solvent molecule are coordinated to the metal ion of the inorganic salt solute. Fifth, ammonolysis or ammonialytic reactions or solvolysis or solvolytic reactions. We have already said that the solvolytic reactions taking place in an aqueous medium and liquid NH3 are called hydrolysis and the ammonolysis or ammonialytic reactions respectively. In hydrolysis, H2O is used as a solvent, while in ammonolysis, ammonia is used as a solvent. Examples of hydrolysis: first, hydrolysis of CuSO4 and SO2Cl2. In the hydrolysis of CuSO4 and SO2Cl2 solutes, the concentration of H3O positive is increased. Second, hydrolysis of AlCl3, Cl2 and OPCl3. Third, hydrolysis of alkali metal hydride. Examples of ammonolysis: first, ammonolysis of SnCl4, SiCl4 and SO2Cl2. In the ammonolysis of SnCl4 and SO2Cl2, the concentration of NH4 positive is increased. Second, ammonolysis of alkali metal hydrides and oxides. The ammonolysis of alkali metal hydrides and oxides gives alkali metal amides. In this reaction, the concentration of NH2 negative ion is increased. Third, ammonolysis of TiCl4. Ammonolysis of TiCl4 is in presence of excess of liquid ammonia produces TiNH2O. This reaction takes place in steps. In each step, chlorine atom of the salt undergoing ammonolysis is replaced by NH2 group. Fourth, ammonolysis of alkyl and aryl halides. The ammonolysis of alkyl halides RX, where R is alkyl group and X can be chlorine, bromine or iodine, takes place slowly at the boiling point of liquid ammonia. In this reaction, mixture of primary RNH2, secondary R2NH and tertiary R3N amines is obtained. Fifth, ammonolysis reactions shown by Hg2, Cl2, HgCl2, BX3, AlCl3, PbI2, SiH3Cl. In these reactions, the concentration of NH4 positive is increased. Sixth, complex formation reactions. First, many metal salts react with excess of KNH2 solution in liquid ammonia to form soluble amido complexes. This reaction can be compared with the reaction of AlCl3 with excess of NaOH taking place in an aqueous solution. Second, many metal amides and nitrides dissolve in the excess of KNH2 in liquid ammonia to form soluble amido complexes. Seventh, redox reactions. Redox reactions in which liquid ammonia is involved can be studied under the following heads. First, redox reactions in which liquid ammonia serves as a medium only. Liquid ammonia provides a medium in which various redox reactions can be carried. For example, KMNO4 acts as a weak oxidizing agent in liquid ammonia. It oxidizes KNH2 to N2 and in liquid NH3 and itself reduces to K2MnO4. B. Iodine also acts as a weak oxidizing agent in liquid ammonia. It oxidizes potassium ammonocetanide K4SN NH26 to potassium ammonocetanide K2SN NH26 and itself reduced to Ki. Second, redox reaction in which liquid ammonia itself acts as a reducing agent. Liquid ammonia reduces various substances like O2, CuO, etc. and itself oxidizes to NO. Third, redox reaction in which alkali metals in liquid ammonia act as a reducing agent. Liquid ammonia can dissolve the alkali metals in it. The solution thus obtained contains ammoniated electrons. These electrons reduce various substances. Thus, alkali metals in liquid ammonia are able to reduce a variety of substances and are themselves oxidized to some alkali metal salt. Following examples illustrate the reducing property of alkali metal in liquid ammonia. A. Sodium to liquid ammonia reduces ammonium salts. B. Potassium in liquid ammonia reduces nitrous salt. C. Sodium in liquid ammonia reduces elemental sulfur to sodium sulfide. D. Lithium and sodium in liquid ammonia reduce elemental oxygen to their peroxide, while other alkali metals give their peroxide as well as superoxide. E. Sodium in liquid ammonia reduces CuI to Cu. F. Potassium in liquid ammonia reduces KMnO4 to MnO and is itself oxidized to KNH2. G. Sodium in liquid ammonia reduces ZnI2 to NaZn4 and itself oxidized to NaI. H. Excess of potassium in liquid ammonia reduces K2NiCN4 and PtNH34Br2 to K4NiCN4 and PtNH34 respectively. 8th, dissociation of weak acids by liquid ammonia. Since liquid ammonia has strong proton accepting ability, it accepts a proton from weak acids like CH3COOH. CH3COOH is completely ionized in liquid ammonia and hence acts as a strong acid in liquid ammonia. 9th, reactions in which ammonia accepts a proton. Pyrolysis. Ammonia is a powerful proton acceptor to form NH4 positive ion. For example, first NH3 picks up proton from H2O to form NH4 positive and OH negative ions. The high solubility of NH3 in H2O or of H2O in NH3 is due to the above reactions. Second, CH3COOH is a weak acid in H2O but shows strong acidic character in liquid ammonia because NH3 picks up a proton from CH3COOH to form NH4 positive ion. Third, urea, NH2CONH2 and acetamide, CH3CONH2 are weakly basic in aqueous solution but show acidic properties in liquid ammonia. Since these compounds can be donate a proton to NH3 to produce NH4 positive ion. Fourth, sulfanic acid behaves as a dibasic acid in liquid ammonia. Here it may be noted that NH2.SO2.OH act as a monobasic acid in aqueous solution since only OH group present in this compound donates a proton to H2O. Fifth, AgNH2 behaves as a weak base in aqueous solution but in liquid ammonia it behaves as an acid. In all the above examples of concentration of NH4 positive in liquid ammonia is increased. Hence, according to Caddy and Esley concept of acids and bases, all these substances behave as acids in liquid ammonia. Advantages of using liquid ammonia as a solvent. First, we have seen above that alkali metals without reacting with liquid ammonia are soluble in this compound. This dissolved alkali metal can be recovered by evaporating the alkali metal liquid ammonia solution. Second, the alkali metal liquid ammonia solution contain ammoniated electron and hence these solution act as a strong reducing agent. Third, we have seen under the study of precipitation reaction taking place in liquid ammonia that these reactions can be used to precipitate metallic halides, sulfides, alcoholates, amides, amides and nitrides. Disadvantages of using liquid ammonia as a solvent. First, low temperature or high pressure is necessary while working with liquid ammonia. This is because of the fact that liquid range for liquid ammonia is from minus 34 degrees Celsius to minus 77.7 degrees Celsius. Second, liquid ammonia is hygroscopic in nature and hence all the reactions must be carried out in the sealed tube. Third, liquid ammonia has an offensive odor and hence the use of liquid ammonia as a solvent and as a reaction medium requires special technique. Liquid sulfur dioxide. Introduction. Liquid SO2 is a non-protonic solvent because it cannot give a proton on self-ionization. Under normal temperature and pressure, sulfur dioxide is a gas but can be readily liquefied. It has a wide liquid range from minus 10 degrees Celsius to minus 75.5 degrees Celsius and hence can be used as a solvent. Its dielectric constant is low and hence it is poor solvent for ionic compounds but act as a good solvent for covalent compounds. Solubility of various substances in liquid SO2. A. Solubility of ionic compounds or inorganic salts. Iodines and thiocyanates are the most soluble. Sulfates, sulfides, oxides and hydroxides are practically insoluble. Many of ammonium, thallium and mercuric salts are soluble. B. Solubility of non-ionic compounds or inorganic and organic covalent compounds. Covalent halides like IBr, BCl3, AlCl3, AsCl3, PbR3, CCl4, SiCl4 and SnCl4 are soluble in liquid SO2. Organic compounds like amines, ethers, alcohols, benzene, alkenes, pyridine, quinoline, halogen derivatives and acid chlorides are soluble. Alkanes are insoluble. C. Solubility of metals. Metals are insoluble in liquid SO2. D. Conductivity of salt solutions in liquid SO2. It has been found that the conductivity of electrolyte solution of salt containing Na positive, NH4 positive, K positive and etc. increases with increase in the size of these cations. Thus, the increasing order of conductivity is sodium, then NH4 positive, then potassium, then CH3 3s positive, and then CH3 4NHN positive. The conductivity of some anions increases in the order SCN negative, then ClO4 negative, then Cl negative, and then I negative is the highest. Auto-ionization of liquid SO2. Self-ionization of liquid SO2 takes place as follows. When we compare that self-ionization of liquid SO2 with that of water and liquid NH3, we find that SO2 positive ion is analogous to H3O positive and NH4 positive ions, while SO32 negative ion is analogous to OH negative and NH2 negative ion produced by the self-ionization of H2O and liquid NH3 respectively. Thus, all those compounds which contain or make available SO2 positive ions will act as acids in liquid SO2. Similarly, all those compounds which contain or make available SO3 2 negative ions will behave as bases in liquid SO2. The above discussion shows that since SOCl2, SOBr2, SOSCN2, etc. give SO2 positive ions in liquid SO2, they behave as acids in this solvent. On the other hand, the substances CS2, SO3, NCH3 whole twice, SO3, K2SO3, which give SO3 2 negative ions in the solvent, act as bases. Chemical reactions taking place in liquid SO2. The chemical reactions that take place in liquid SO2 can be following types. First, metathetical or precipitation reactions. Some of the precipitation reactions occurring in liquid SO2 are given below. First, thionyl chloride in liquid SO2 has helped to precipitate many compounds. Second, examples of other precipitation reactions that can be carried in liquid SO2. Second, acid-base neutralization or salt formation reactions. In liquid SO2, acid-base reaction is that in which a compound containing or making available SO2 2 positive ion acid combines with a compound containing or making available SO3 2 negative ion to form a salt and the solvent. It may be seen from the equation 1 that the neutralization reaction in liquid SO2 can also be defined as the combination of the solvent cation and the solvent anion to produce the solvent. The acid-base reaction between SOCl2 and CS2SO3 given above has been explained on the basis of self-ionization of liquid SO2 shown below. However, there is no experimental support for the existence of SO2 positive ions. Thus, in order to explain the acid-base reaction, the self-ionization of liquid SO2 is not required. The acid-base reaction can be explained on the basis of coordination model, according to which the reaction proceeds through the following steps. Third, amphoteric behavior of salts in liquid SO2. First, amphoteric behavior is shown by Zn2 and Al3 salts in liquid SO2 as is evident by the reaction of K2SO3 with ZnCl2, ZnSO3, Al2SO3 twice and AlCl3. Second, AlCl3 react with NaOH which act as a base in aqueous solution to form the precipitate of AlOH3. AlCl3 also react with CH3 for whole twice SO3 which act as a base in liquid SO2 to form the precipitate Al2SO3 thrice. The precipitate of AlOH3 thrice dissolve in the excess of NaOH base in aqueous solution in aqueous medium to form the soluble hydroxo compound. Similarly, the precipitate of Al2SO3 thrice dissolve in the excess of NCH3 4 twice SO3 in liquid SO2 to form the soluble complexes. From the soluble complexes, NaAlOH4, AlOH3 can be precipitated by adding HCl in aqueous solution. Similarly, from the soluble complex can be precipitated by adding SO2Cl2. Third, GaCl3 also shows amphoteric behavior in liquid SO2. This can be explained in the same way. Fourth, solvation reaction formation of solvents. Like water and liquid ammonia, liquid SO2 also forms addition compounds with solutes. These addition compounds are called solvates and contain one or more molecules of sulfur dioxide as sulfur dioxide of crystallization. Example of some solvates formed in liquid SO2 are Li.2SO2, Kbr.4SO2, Mi.4SO2, Mi2.4SO2, AlCl3, 2SO2, KCNS, NSO2, Cl2.SO2 and 2SO4.3SO2. In the formation of solvates, SO2 molecules act as a Lewis acid electron pair acceptor and the solute act as a Lewis base electron pair donator. With the decrease in the Lewis base character, the solubilities of alkali metal halides in liquid sulfur dioxide also decreases in the order. Iodine the highest, then bromine, then chloride and then the fluoride. Fifth, solvolytic reactions or solvolysis in liquid sulfur dioxide. Solvolytic reactions of the salts in liquid sulfur dioxide are much less common than in many protonic solvents. Some such reactions are given below. In these reactions, concentration of SO2 positive or SO3 2 negative is increased. Sixth, complex formation reactions. First, when the solution of the salts like AlCl3, ZnCl2, etc. in liquid SO2 react with the excess of a compound containing SO3 2 negative ions, soluble sulfito complexes are formed. Second, solubility of I2 in liquid SO2 is greatly increased when Ki or RBI is added to it. This is due to the formation of complex compound Ki3 or RBI3. Third, when HgI2 or KdI2 is dissolved in liquid SO2 in presence of Ki, the solubility of these iodides is increased due to the formation of K2MI4, which is a complex compound. Fourth, other reactions showing the formation of hexahalo complexes in liquid SO2 by the action of covalent halides on alkali metal halides are given below. Seventh, redox reactions. Liquid sulfur dioxide itself does not act as a strong oxidizing or reducing agent. It serves only as a medium to form any redox reaction. For example, a sulfide in liquid sulfur dioxide reduces iodine to iodide and itself oxidizes to sulfate. B. SbCl5 in liquid sulfur dioxide oxidizes Ki to free I2 and itself reduces to SbCl3. C. FeCl3 in liquid SO2 oxidizes Ki to free I2 and itself reduced to FeCl2. 8th, organic reactions in liquid sulfur dioxide. Organic reactions where relatively inert and non-inflammable solvents are required, liquid SO2 serves as the best medium. Some of the important reactions are: first, sulfonation. Good yields have been reported for the sulfonation or aromatic compounds in liquid SO2. B. Bromination. Both for addition and substitution reactions with bromine, liquid sulfur dioxide has been used. C. Friedel-Crafts reactions. AlCl3 is highly soluble in liquid sulfur dioxide and is therefore a preferred solvent over ether, which is highly inflammable. So this was all about non-aqueous solvents.